Very good afternoon, everyone. Have you ever wondered if you left a cup of hot coffee on the table and noticed how it cools down quickly at first, but then slows down as it's closer to the room temperature? Or have you ever wondered how detectives estimate the time of death based on body temperature? All of this is explained by Newton's law of cooling, which helps us understand how object loses heat over time. So today in this lecture, I will talk about what Newton's law of cooling is and how it works, the connection to the first order differential equation, a simple real world example with cooling coffee, some practical applications in science, engineering, and forensics. So let's begin. I hope everyone is ready with their notebooks and pen so that it will give a more efficient learning will happen so that whenever you're learning, you're also writing and understanding at the same point. So now we will start the lecture. So, what is Newton's law of cooling? In a very simple terms, I will first explain you all. Firstly, imagine you take a hot pizza out of the oven. At first, it's very hot and it cools down quickly. But after a while, it gets closer to room temperature. It cools. So, as it gets closer to room temperature, you must have observed it cools much slower. Why does this happen? So this is what Newton's law of cooling tells us. The bigger the temperature difference between an object and its surrounding, the faster it cools. And as the object cools down, the temperature difference gets smaller and the cooling slows down. This is why the also this is the reason why hot coffee first heats initially faster but takes longer to reach the room temperature. Mathematically, this cooling process follows a first order differential equation, which we will discuss next. So here we will see what the statement for the Newton's law of cooling, and I expect everyone to note down. The Newton's law of cooling states that the rate at which an object cools is proportional to the difference in the temperature between the object and its object surrounding. As I explained with an example of the coffee, how it cools faster but takes slower, but it takes the difference of the temperature gets smaller, and since other cooling slows down. Here is the formula for Newton's law of cooling, that is d capital T by small t is equals to k T minus Ts. So we'll define the capital T as temperature at time t, Ts as surrounding temperature, and K is the cooling constant. So now we will understand how it is connected to the first order differential equation. So, what is first order differential equation? It is an equation that involves a function and its derivatives. So we know that Newton's law of cooling is written as d of capital T is by small dt equals to k T minus ds. So this equation is a first order differential equation because it contains the rate of change of temperature and involves the first order derivative, no second or higher order derivative. To find the actual temperature function that tells us how temperatures changes over the time, we will now solve this equation. Now we will see the mathematical derivation of Newton's law of cooling. So firstly, we will start with writing the equation cap dt by capital dt by small dt is equals to k of t minus tx. So we will first rearrange all the t terms to one side so that it would be very easy for us to solve. So here we took d capital T divided by t minus ts, all the t terms to one side, and k and also so that it would be easy. So it's equals to k of dt, k into dt. Then on integrating the both the side, we get TF minus T. Tf minus Ts is equals to T divided by T naught minus Ts minus K into T. So uh, after this, we will see the final formula of Newton's law of cooling with exponenting and doing. Then we will get the Newton's law of cooling, the formula, and apply the initial condition. So from here, we will see this equation helps us predict how an object's temperature changes over time. So then we will see the graphical representation of Newton's law of cooling for better understanding, so that we will also have a visual image. So here I took a graph, and here also we see in the graphical presentation that how initially the temperature changes, how initially the temperature changes, and then how gradually it decreases. So then here also we use some real world application to solve a question of cooling coffee. So here we saw the initial temperature is 80 degrees Celsius, room temperature is 20 degrees Celsius, the cooling constant is given. We'll substitute and put everything on the equation, and the time taken is 10 minutes. So then we found out that it takes 18 minutes for the coffee to cool at 30 degrees Celsius, and after 10 minutes, the coffee cools to 42.07 degrees Celsius. Then we'll see some more applications. So Newton's law of application is used in many fields like forensic science, food safety, engineering and electronics, climate science. And fun fact, did you know that forensic scientists use a thermometer in the liver to estimate how long a person died? This is based on Newton's law of cooling. It's so good that with the law we can use so many things. Then we come on to conclusion. So what do we learn today? We first learned what is Newton's law of cooling, how it explains objects cooling over time, how it is modeled by first order differential equation. We got the formula that helps predict temperature decay. We also dived into some real world applications. Thank you for listening. I would like to hear your thoughts. What else do you think on Newton's law of cooling? Thank you.